Welcome everyone to the paper spotlight. My name is Max. I'm a research teammate at Transformative, jumping in for Alma, who's usually hosting these events. Today with us we have Rudi from BIFO/TU Berlin, PhD student in the domain of big data and machine learning, and he'll introduce himself also in a bit more detail shortly. I think many of you have been already here in the past. We do this event monthly. It's a kind of get-together for the more techy ML-related topics here at the campus, hosted by Mosaics Momentum. We're kind of a machine learning research department / client project business. So I'm working in the research team. We do publicly funded and also internal research in the area of machine learning, of course. I mean, everybody is doing that here. And we host this public event where we bring together kind of people from the Berlin, mostly from the Berlin machine learning crowd, research crowd. So this is the most tech-heavy of the events I think we do at the campus. Those who've been here really get into the nitty-gritty of the technical details. So if you're interested in this kind of moment and like today's, please check out this event recurs every month. I think usually on the first Tuesday. With that, please, Rudi, take it away, and I'm looking forward to your talk on Mosaics on big data.
Thank you very much, Matt. Yes, hello, my name is Rudi Poepsel Lemaitre, and today I have the honor of introducing you a little bit of what we've been researching and doing in my department at the TU Berlin in the DIMA group, and also to give a brief motivation about what's the goal of big data technologies in today's landscape. So let me first introduce myself. So I originally come from Bolivia, so a little bit far away from here, but I already have experienced Berlin very truthfully over the years. I did my bachelor's and my master's at the TU Berlin. And then during my master's, I had the big opportunity to lead my own research project funded by the Software Campus Initiative. And then later on, I decided to continue with my PhD at the TU Berlin. Currently, I am focused on researching how to integrate data protection policies into database systems in an automatic way, such as the GDPR. However, I won't be able to show a lot of details of my own research, but we can discuss about that later on the networking event afterwards, if you're also interested. So let's start. First of all, I want to make this also a little bit general and motivational. So the main idea is that at some point in our lives, sooner or later, we need to decide where do we want to make the biggest impact, either in the industry or in the science and humanities sector. So both of these sectors are not mutually exclusive, and they actually inspire and contribute each other with many different applications. And in the center of these two sectors, we have seen a growing popularity of two big technologies, which are data science and artificial intelligence. Both of these, again, complement each other and need each other. And in its heart, they have essential algorithms that require big data management and also machine learning algorithms in order to gain the insights and the capabilities that we require in everyday applications. But how do we land here? How data became so important? And in order to understand that, we need to go a little bit back and understand how we actually faced research since the start of the millennia. So first of all, about 1,000 years ago, we performed something that was a more empirical research. So we were describing natural phenomena. Galileo Galilei was simply observing phenomena, writing this, and trying to formalize as much as possible. But with the means back then, it wasn't possible to describe everything to a full detail. That's what started to happening about 100 years ago. We took a more theoretical approach. Now we were actually modeling and generalizing all these phenomena using mathematical formulas. These formulas were describing accurately what we could expect from the future. Based on these formulas, over the last decades, we started a computational approach. We started simulating this phenomena. We started actually looking at what could happen and how we can use math in order to predict the future. However, this has shown that at the end of the day, these formulas oversimplify actually the natural phenomena and the natural spectrum. And at the end of the day, we need more data. We need to jump from the assumptions of a perfect world without noise and actually try to take into consideration all the measurements that we can actually gather and use this in order to improve our predictions. And that's where we are nowadays. We have massive amounts of data generated by measurements and simulations, and we need to perform some kind of data exploration task using software and the knowledge stored in our computers. And this is valid for any research field, not only data scientists, not only machine learning experts. So people started claiming, based on this trend, that data was becoming the new oil. Data was required everywhere. Data had an immense value, and just as oil, it was becoming a fundamental resource in the industrial age. Data was becoming an essential resource for our everyday applications and our everyday life. So, however, what we think actually is that the main concept behind this phrase of data is the new oil is that data was valuable, but if not refined, it cannot be really used. And where the phrase actually breaks down, so we claim that actually data is not the new oil, is actually when we think about availability and reusability. So first of all, data is everywhere and everyone has the means to capture it. So unlike oil, where actually you needed to be actually lucky enough to live in a country where dinosaurs happened to die millions of years ago, anyone can actually take their computer and start collecting data of a specific sensor or start monitoring an open source data set on their own. And second of all is that data is not only reusable, but actually its value grows the more we use it. We need to use data, gain more insights, and then we are actually enriching data and enriching our knowledge step by step. That's why we claim actually that data is not the new oil, but actually the new soil. And in that sense, a new production factor for modern industry. So like soil, we firstly collect the soil, then we work it with some specific tools, we treat it with some fertilizer to enrich their properties, then we exploit it, and then we can collect the soil again to repeat this process all over again. The same happens with data. We collect some data. First of all, we need to prepare this data, doing some data cleaning tasks, some data integration. Then we can actually enrich this data using external knowledge, external data sets, and then we can actually set it for the process of our algorithms and then gain new insights that later on will generate new knowledge bases, new data sets that then we can still reuse. So at the end of the day, this is the life cycle that we want to see in data. And who is in charge of all of this? Actually, the data scientist. But being a data scientist is actually quite a burden. It's quite difficult. First of all, we need to know a lot about technologies and systems. We need to know a bunch of theory about databases, relational algebra, which kinds of system architectures there are, some concepts about optimization, hardware properties, parallelization. So there is a lot of knowledge that the data scientists need from the technical part. Then we have the algorithms and methods spectrum. Here also a data scientist needs to understand the mathematics that needs to be applied in order to really gain the most out of this data that was collected. However, nothing makes sense without some domain area knowledge. We need some domain area knowledge in order to know what data to use in order to succeed in a specific application. At the end of the day, finding a data scientist with a good knowledge in all of these areas is quite rare, quite valuable, and that's why we tend to ask for a lot of money to companies, but this is not scalable. So at the end of the day, a data scientist cannot actually solve all of these problems, and actually training a person to do all of these things at once perfectly is quite unfeasible. So what we can do is actually use some technologies. So there are big data technologies that try to do our life easier, try to actually make this whole process a little bit simpler for us. However, we could rephrase the task to now we have a problem and we need to choose the right tool in order to make this problem easier. So we have this beautiful big data landscape with different technologies. Quite difficult. This was in 2012. This is our big data landscape now. So if the decision was difficult in 2012, imagine how difficult it is right now. And this is a tendency that is going to increase. So we are going to have more technologies, and this increment of over 1,200 technologies that are acknowledged by this benchmark, because at the end of the day, the real amount of technologies is much higher, it's going to be increasing with the time. And we need to actually be able to differentiate and choose the right technology in order to make our lives easier as technical experts, and also the lives easier of the domain expert that will be working besides us for the different applications. Just as a brief description of what we call a big data technology are the tools that are designed to store, process, analyze, and manage large and complex data sets. The most notable open source big data technologies that we can mention are actually Apache Hadoop, which actually started this whole trend of processing data out of scale, out of core. Then we have Apache Spark, Kafka, and Flink as next generation platforms. And then we have another category of new SQL databases such as MongoDB, Cassandra, or Redis. But what does all these tools want to do? So what are their goal actually into simplifying our lives? So first of all, we have a data scientist that has a very specific task in mind. So it will extract some information, it will integrate this information, it will perform some analysis, and then it will build a model based on this data. So the first task that the data scientist will do is a specification task. The specification task uses declarative languages that tell what to do and not how to do. We need some automatic optimization on this step to actually choose the physical operators that will actually perform this task on the computing infrastructure. The computing infrastructure will gather this information specified by the data scientist, and finally, we'll have the data processing step. Now the system will choose for itself many different hardware properties and algorithms that actually we shouldn't care about. We shouldn't care quite a lot about parallelization, distribution, or caching algorithms. This should happen as automatically as possible. So at the end of the day, a big data technology has one of these two goals, or maybe both, but it's either to improve the human efficiency. We want to make it easier for a user to define what they want to achieve. We want to make it easier to solve a specific problem, or we want to improve the technical efficiency. We want things to run faster. We want to be more efficient. And these are the two big parts where big data technology wants to have an impact in order to be usable for an application. Based on this mentality, one of the best examples that we can give you from our group is a Stratosphere. The Stratosphere was a general purpose programming engine that tried to merge this idea of and contributions of a system with a database execution. So first of all, we draw a lot of knowledge that we already had about database technologies, like relational algebra, declarability of queries, query optimization, and robust out-of-core computation. And then we also gathered some knowledge about the newest back then MapReduce technology, which was heavily criticized, but at the end of the day, they also did some things right, which was actually on the engineering spectrum, how to scale, how to provide user-defined support for user-defined functions, how to look at complex data structures, not only relational data, and how to read and how to have a schema on read. So at the end of the day, we also created some extra contributions like iterations, advanced data flows, general API, and native streaming, and this gave birth to our biggest baby until now called Apache Flink. Apache Flink is an open source stream processing framework for distributed, high-performing, always available, and accurate data streaming applications. So first of all, have you ever used Flink before? No? Okay, so the biggest difference between streaming processing and batch processing is actually the nature on how data is arriving. So usually when you are in a batch processing scenario, what you have is already a data set that you can store in your computer and then read it whenever you want and do all the processing whenever you want. The idea of a streaming application is that you are generating data all the time. You need to consume this data on the fly. You need to start thinking data not as a bounded resource, but as an unbounded resource. And that was actually the main concept that we were trying to target with Apache Flink. Apache Flink supports both bounded and unbounded data, but what it really makes a difference is that we have this event time semantics in order to provide accurate and high efficient real-time computation. We also have high fault-tolerant guarantees, and we can actually scale out to thousands of nodes with very good throughput and latency with exactly one semantics. But again, what was the concept that we had in mind back then? First of all, we wanted the life of the user to be easier. We created an API that was easy to use, that used higher order functions, and that allowed the data scientist to specify its own user-defined functions. Using this basic this declarative language, we could actually perform some automatic optimization using an algebraic model and a cost model and create what we call a data flow graph, a plan that we are trying to execute on a hardware resource. And during runtime, actually Flinks take care of all the rest. So you don't have to care about anything in the infrastructure. You just submit your job and Flink will take about fault tolerance, will take care about resource management. It will distribute the different operators. It will monitor the health of these different workers and will perform basic tasks of memory management, state management, etc., etc., etc. So we are working with contributions about the both spectrum. We wanted to improve human efficiency and at the same time also improve the technical efficiency of our applications. Once again, what is the impact of this automatic optimization? So imagine you are just working on your computer and you're defining a streaming application. First of all, what you want to do is actually test if this application is actually working or not. If you can compile it, if you can deploy it, and you test it simply in your notebook with a very small data set. Now that you are happy with it, you say, okay, now this is ready for deployment, and now I will execute it on a big data cluster. However, you didn't change the program. So you simply define it once, you were making sure that this works, and now you can deploy it on the cluster. Based on the performance on the cluster, you can say, oh, you know what? I made a small mistake based on the assumptions that I took. So let me change something and let me execute this in a larger cluster for some later analysis and et cetera, et cetera. At the end of the day, what we achieve is that declaring once, you can run it everywhere and the hardware optimization will be taken care of. Because let's be honest, who wants to hand tune this? So doing all this hand tuning for a plan, for an application every single time, for every single hardware that you have is actually very inefficient. At the end of the day, this translated into a huge impact also in the industry. We have a lot of proud Apache Flink users around the world. And where we can see also in their real world scenarios that our solution was robust. So we have Alibaba running Flink on a 1,000 node cluster. We have also King using jobs with over 30 operators with gigabytes of state. And at the end of the day, all these cases show that our theoretical ideas actually had an impact in the real world. And that's what we want to achieve. We also have a very strong community. This is a little bit outdated. This is from 2020. But Alibaba actually pushed the root company from Apache Flink, Data Artisans, back in 2021. And yeah, but this is the success story that I wanted to tell first. So everything started at the TU Berlin with a simple vision, a simple theoretical vision. We had an idea, we had the motivation of where do we want to improve the life of our data scientists in the future? Because at the end of the day, back then, data streaming wasn't that hot, but nowadays the current applications require this real-time processing of data. And this will be an increasing tendency on the future. And all of these steps in the middle is exactly what we try to do at academia. We want actually to try to find problems in the real world and try to solve them using the strong, knowledge of the theory behind all of these practical problems. So now let me spring to our newest generation. So of course we cannot live from the successes in the past of Apache Flink. So we have to move on. And now we are targeting a new real world scenario, which is the Internet of Things. But what is this exactly? So it refers to a network of interconnected devices that collect and exchange data. And actually, in a specific hierarchical structure where we have different layers of data processing until we achieve the cloud. So we have heterogeneous compute resources. We can have autonomous cars. We can have cell phones. We can have some sensors on the highway. And then we just collect this data and start pushing it into higher layers of our hierarchy until achieving the cloud. So, and this can be diverse based on the applications and the workloads. And in order to make it even more difficult, we can even assume that this can be geo-distributed. So we can assume that we are working on a larger, conceptually on a larger application and actually have the deployment on different countries, different continents, and then we even have other kind of challenges such as data protection policies, and et cetera, et cetera. So what we want to do is actually give support to this new kind of topology. And for this, we are proposing NebulaStream, which is data management for the Internet of Things. We want to have an end-to-end open source data management system that actually can manage all the main challenges of this topology and actually try to, again, improve the human efficiency of the data scientists using this tool. We want to make it general purpose. We want to make it as simple as possible to define these problems. And at the end of the day, we want to have a high performance and while keeping it easy to use. The basic architecture of NebulaStream, so this is really, really basic, but at the end of the day, we have simply a NebulaStream coordinator that is actually taking care about every coordinating and managing task of the NebulaStream workers. And the NebulaStream workers are the ones in charge of carrying out the low-level computation and consumption of the data generated by the edge devices. Now I'm gonna talk about a simple use case. For example, we have the query lifecycle and what we call the query merging. Imagine you have a query where you are simply accessing data from two different sources, from two different sensors. You're joining this data and you're performing some analysis task on top of this joint data. However, you're not the only one submitting queries into this network. There are different people trying to access different kinds of information and consuming data at the same time. So at the end of the day, what you will end up having is a global query network. So you are accessing from the same source, but you are performing a different task. This combined with the I/O topology, what I showed you before, we have the different sensors, we have the intermediate data processors, and we have our cloud provider. Based on this, we have to take the very difficult decision of where do we place these different operators. We could try to put everything on the source and try to just push end results in order to leverage the utility of the network, but this will generate a huge load to the sources. However, we can distribute this load and push the operators up or down in the hierarchy, which usually have bigger resources and perform the most expensive operations on these devices instead of the edge devices. And then we can deploy it. We can deploy it on the real world scenario. We can say that these are different buses around Berlin, and you are doing this analysis task around the area of Berlin, and you are seeing how these different buses interact and collect the data within each other. However, since these buses move, since these buses can have sensors that start failing and some queries that will change, we need to be able to do this query merging and query optimization quite often. We need to be able to be prepared for changes and to change this topology and this distribution, this execution network as often as it's required. So thanks to query merging, we can see that we can improve the utilization of the network. We want to avoid sending way too much data because at the end of the day, network is the biggest bottleneck. And this also allows us to show that this combined with the single core performance of NebulaStream, we can achieve very, very high performance. So here we are seeing a small benchmark of comparing NebulaStream with state-of-the-art systems on a single core. And here, the main advantage of NebulaStream is that everything is written on C++. So we want to be able to run code, compile code as close to machine code as possible and perform high-tailored code that can be executed on any kind of device. And this can be also shown on this plot where we can deploy NebulaStream either on a very small Raspberry Pi with 4 cores, or we can also deploy it on a very high-performant cloud system like the Xeon Platinum with 24 cores. So we have this flexibility. We use the same compiler for this, for any of these hardware technologies. And at the end of the day, the user doesn't need to take care about the optimizations for each of these for these hardwares. We are just starting, so we are planning for the open source release on the upcoming months, but we have already more than 30 contributors with over 250,000 of lines of code, which include Java, Python, C++, but this is just the beginning. We hope that we will achieve something similar to Apache Flink. And that's the main takeaway of my talk. At the end of the day, what we want to achieve is always being prepared for the next generation of big data technologies, being able to foresee the applications of the future and try to solve with our theoretical knowledge the problems that real world applications will face on a daily basis. And that's it. Thank you very much.